Welcome! These videos were recorded while I taught topics in Econometrics over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. That explains why you may notice some unnatural transitions and why the videos are shorter than a normal lecture. But hopefully you will enjoy them anyway. Bye now. We should start with lecture 11. Today we're going to talk about the uniformity of the t-test. And so, if you recall, last class we started our discussion on uniformity, okay? And we talked about the uniformity, the definition of uniform size control, and then actually we talked about what size was as opposed to rejection probability and the null. And then we discussed this famous example by Bahadur Savage. We actually described the main result, and then we proved it. After doing that, we talk about the result by Romano with some extensions to that. But perhaps the most important takeaway was that it was impossible to test hypothesis about the mean, and in particular that the t-test, to test hypothesis about the mean had size equal to 1. And that was concerning because, again, we use the t-test all the time for regressions, for you name it, right? So then, coming here and tell you that you cannot use the t-test to test hypothesis about the mean is concerning. So today we're going to, as I said, we're going to save the t-test, okay? We're just going to go back and save it. And we're going to start the discussion by considering distributions that will violate the conditions from Bahadur Savage first. And I'm going to do one of such example. I mean, other examples exist, and I actually used to give some of those in problem sets, but you're not going to do that this year. And it's possible to say that even by removing some of the conditions in Bahadur Savage, the t-test still fails massively. Though remember, the result by Bahadur Savage is there doesn't exist a test. So you can show that when you remove some of these conditions, there are other tests that end up working, for the situation at hand, but not in particular the t-test, So today, as I said, I'm going to show one of those examples, which is distributions of compact support. Now we're going to see that if you just restrict attention to non-parametric family of distributions that take values in a compact set, the t-test still has the problems that we described last time, And this is quite restricted because, we talk about tails, right? And then people always associate tails with things that are far from zero, going to infinity or negative infinity. Well, we're going to try to understand better what the problem behind the t-test is. And then we're going to introduce the family of distributions that are called uniformly integrable, which a subset of those that are important is going to be distribution with 2 plus delta moments. We're going to talk about this relationship. And we're going to show that this is a large family of distributions that renders the t-test uniformly valid. And so we're going to see how that relates to the central limit theorems that we know. And we're going to talk, and that's going to be the hardest part of today's class, about law of large numbers that will work under this type of assumptions. And then we're going to put the two things together to show that the t-test is uniformly valid. And then, that's about size. And then we're going to say, does it have power? Because it could be that we show that the test controls size and has no power. We're going to show that the t-test has non-trivial power. So put everything together, and then we're going to be able to save the t-test. And we're going to learn why so often you're going to see papers that will assume 2 plus delta moments, or a little bit more than 2 moments, and that's what's going on. So, last class we covered the important result by Bahadur Savage and some generalizations. The class of distributions that satisfy the conditions in the theorem is large, which is, remember, these conditions that say, for example, give me a number in the real line and I can find a distribution that has the mean equal to that number. The example is the class of distribution with second moments, and actually the class of distributions with infinitely many moments are families that fit into the Bahadur Savage result. We concluded the failure of the t-test was not special to the t-test. and that there was simply no reasonable test for this type of testing problems when you wanted to be non-parametric over a really large family of distributions. And we said also that the mean mu of P is quite sensitive to the tails of P, and we said that one sample yields little information about the tails. Today, we're going to study conditions to save the t-test. But before doing so, we're going to try to understand a little bit better the implications of these three conditions in Bajel-Savage. So, if we restrict attention to distributions with compact support, well, that, as strong as it looks, okay, does not save the t-test. It breaks the Bajel-Savage result. You can show that there's a test that exists and works well, okay? But unfortunately, it just doesn't save the t-test. And remember that one of the conditions in Bajel-Savage was, for any, something like this, for any m in the real line, there exists P in bold P such that mu of P was equal to m. Well, this condition we're violating here because, the mean of a random variable that takes values between 1 and 2 can only be between 1 and 2. Okay, so once we consider distributions that have a compact support, we're violating these conditions. So we're gonna let x1, xn be IID according to P, and then the t-test, we're gonna consider the one-sided version because it's simpler, okay? And we're gonna be testing whether the mean of this random variable is 0 versus the alternative that is positive. And as we did last time, I'm gonna just write the t-test like in this way, where we just have sigma on the right-hand side. Well, let P be the distributions supported on -1, 1, just as an example, and bold P naught the subset of those with mean 0. Then, using exactly the same arguments we used last class, you show that the size of the t-test is 1. What's the argument? Is exactly, I rewrote it here so that you have it, but we did it last time. You fix n, fix any, sorry. You fix n, you fix any c, and then you choose Pn such that 1 of Pn is equal to c, and then you let P and C the distribution that places mass 1 minus P at P and mass P at -1 minus P, so that the mean is 0, and then this is the example. And remember that we learned then with probability C, we have that xi was equal to Pn for all I. We also learned that a square root n bar was square root Pn, which was positive. And we learned that sigma hat n was 0. And so the t-test here was 1. So with probability at least C, the t-test rejects. And then look at this example. It's just a distribution with support on -1, 1. So we don't need, in essence, another example to prove this statement that I have in this line. This example works as it is because it was already an distribution supported on this particular interval, -1, 1. Now, what's going on then? Well, today we're going to start to get sort of like more in detail about this. The problem here is that we have no control over this Q-ness of this distribution over here, right? So if you compute this Q-ness, which is the expected value of x cubed divided by sigma cubed, according to this distribution P and C, well, this is a 2-point mass distribution, so it's quite easy to obtain. You do some algebra, and then you get Pn squared plus 1 minus Pn squared divided by square root of Pn times 1 minus Pn. And this converges to infinity along this sequence, okay? So as we said intuitively last time when we talk about tails, what happens is that the distribution puts a lot of mass, okay, close to 0, and, just some tiny mass in a point that is far away, okay? And that affects the skewness. In fact, as I wrote here, the problem appears the moment we exceed the second moment. So if you can see a little bit more than 2 moments, and here I'm going to call it 2 plus delta, the same phenomenon happens. So just take the expected value of the absolute value of x to the 2 plus delta divided by sigma to the 2 plus delta. Okay, then you now have this expression over here. Again, along this sequence, this goes to infinity. And this is a condition that will be meaningful later. But what I want to say here is that notice that there's something tricky in the terminology. People always say 2 plus delta moments, 2 plus delta moments. We always mean moments that are rescaled by the variance. Okay, so you're always thinking about the random variable divided by its standard deviation. Okay, so when you take 2 plus delta, you take 2 plus delta of the recenter and rescale. In this case, the mean is 0, but the usual, x minus mu divided by sigma. That's the object that you want to have 2 plus delta moments. Okay. Notice that if I were to just look at the numerator here, this numerator is fine, doesn't go to infinity. You see that. So it's just a ratio of how things, it's just a definition that depends on the ratio. Now, on the example, before moving on, let's make the previous example more convincing to ensure that the underlying distribution is continuous and the observations are distinct. Okay. This is to address this issue that I said last time. Sometimes people say, oh, look, this is fine, but this example is just a 2-point mass distribution. It looks kind of weird. Well, let's see. We're going to extend the example as follows. Let x star and I be x and I plus u and I, where x and I has distribution p and c, which is the one that we described before, and u is independently uniform over negative tau n and tau n. What is tau n and negative? What is tau n here? Sorry. Well, it's just a number that is not larger than this. Square root n pn divided by square root n z1 minus alpha. Okay. So notice this. I want to say here. No. We're going to see that this example, where here you see the random variable over here is, it doesn't have to take 2 points. It's continuously distributed. Okay. Or it is, then the same manipulations that we did will hold. So notice that the following. I want to say here tau n is less than pn divided by 1 plus z1 minus alpha divided by square root n. I only took the 1 over square root n divided. And so then this means that I have tau n plus tau n z1 minus alpha divided by square root n less than pn. Okay. And then I have that pn minus tau n is greater than tau n z1 minus alpha divided by square root n, which is positive. So it's sort of like the first thing I want. Okay. So then I'm going to look at two objects. The first one is x bar and n star, the sample average of these random variables. And this is going to be x n n bar plus u bar and n. So with probability at least c, then we have that x bar star and n is, pn plus u bar and n, which is greater than or equal than pn minus tau n. Because, this average, this is a uniform taking values between negative tau and tau. So this is greater than or equal than negative tau for sure. And based on our condition here, star, we have that this is greater than tau n z1 minus alpha square root n. So that's the first part. The average of these random variables satisfy this inequality. Let me look at the sample variance of this guy, sigma square star. But this is 1 over n sum from 1 to n of x star and I minus x bar star and n square, which is equal with probability at least c to 1 over n, the sum 1 to n of u and I, u bar, and n square. Why? Because, with probability at least c, the average of this part of x star equals p, and so p and p will cancel out. So you only get the u's with probability at least c. This is less than or equal. Less than or equal than 1 over n, the sum from 1 to n of u and I square, which in turn is less than or equal than tau n square. Okay. You guys following? Right. So then we can say with probability at least c, we have that square root n x bar and n star divided by sigma hat star n should be, which is the t statistic, is greater than, let's say greater than or equal than Pn minus tau n, which is greater than or equal than Pn minus tau n over tau n, which is strictly greater than tau n z1 minus alpha. Sorry. Whoops, sorry. Apologies. This is square root n Pn minus tau n sigma hat star n n. And now this is greater than or equal. Same object, but I look at the denominator now. This is tau n. And this is strictly greater than tau n z1 minus alpha over tau n, which is equal to c1 minus alpha. So we conclude with probability at least c, the t-test here rejects. And since, c can be anything we want, we're good to go. So, you can write here to be nice A, B, C, and so this is following for A, B, C. Yep. So, in other words, and this is just to say, the example that we did to quote unquote make the t-test reject all the time, was a 2-point mass, but here we're adding some noise. Now we have a lot of other points. The example still works. Okay, just to make it more sophisticated if you want. That's it. Here I had another page to continue the proof, but I fit everything in one line, so that was more efficient. Questions about this? Okay, so we got here. Now we're going to try to save this t-test. We're going to start thinking about distributions with 2 plus delta moments. So I wrote here, good news. The t-test uniformly consistent over a certain large subfamilies of distributions with 2 finite moments. That is, you need a little bit more than 2 finite moments. And in particular, you need this condition that is called uniform integrability. So consider a family of distributions ball P on the real line, satisfying this condition over here. Then I'm going to read slowly. Forget about the supremum and this first, the expected value of x minus mu squared divided by sigma squared times the indicator that x minus mu divided by sigma absolute value is greater than lambda. Well, you take the supremum over all the elements in this family and you take lambda to infinity. This is equal to 0. Okay. And this, if you just look at this condition, this is how we control, in a way, the details. Okay. And notice that this is a condition that is about the random variable y, which you can define as x minus mu p divided by sigma p. And this is the object here, that here and over here would be the absolute value of y squared, and this is the absolute value of y greater than lambda, right? So if you want like a really clean notation to describe this uniform integrability condition. There's another family of distributions that I wanted to know by bold P2 plus delta, which is the set of distributions such that the expected value of y to the 2 plus delta, or if you want x minus mu to the 2 plus delta divided by sigma to the 2 plus delta, is bounded by some constant m. Okay, so this is called the family of distributions with bounded 2 plus delta moments. Okay, and so this family of distributions is a subset of the family of distributions that is uniformly integrable. Okay, and then to see this, let's prove it here because it's very simple. To see this, let y be as before. I wrote right here, x minus mu p divided by sigma p. And note that lambda to the power delta y to the square times the indicator that the absolute value of y is greater than lambda is less than or equal than the absolute value of y to the 2 plus delta. Okay, and so then the supremum of p in bold p2 plus delta of the expected value under p of y squared times the indicator that y is greater than lambda is less than or equal than 1 over lambda delta supremum of p2 plus delta expected value y2 plus delta. Okay, just use this inequality over here, or use it here. So now the family p2 plus delta here is such that this supremum here is less than or equal to m. So this is less than or equal than m divided to lambda over delta. So then take lim as lambda goes to infinity, and then you're done. You show that this family of distributions is a subset of the family of distributions bold P. It satisfies that the limit as lambda goes to infinity of the supremum is 0. So, when people, depending on the papers that you read, you're going to see papers talking about uniform integrability, other papers talking about 2 plus delta moments. The argument for using 2 plus delta moments is that sometimes some researchers will say, well, this is easy to explain to the audience. It's just you have bounded moments done. People are used to those type of arguments. Whereas this condition over here is much harder to interpret. Okay. And then the argument for those that will just use the uniform integrability will say, look, this is the largest family of distributions that we know of, where we can say the t-test. Just why would you restrict yourself to a smaller family? How much bigger is this relative to this? Hard to quote unquote measure. But both will be seen out there. And if you just think about, central limit theorems, you will immediately recognize that this uniform integrability condition is associated with the Lindbergh-Feller CLT, and then this one over here will be associated to the Levy CLT. Okay, so and that's sort of like what's going on. Now, so I'm gonna prove everything today about the uniform integrability, using uniform integrability, because by proving this, of course, we are saying that the t-test holds for 2 plus delta moments by this argument that we did here at the bottom. Okay, let's go. Let bold P be the set of distributions in P that have mean equal to 0. For testing the mean equal to 0 versus the alternative that the mean is positive, the test that is reject when the test statistic is greater than the quantile of a normal, where the test statistic is just the t-test statistic, is uniformly asymptotically level alpha over bold P, as shown in the next theorem. And here's the theorem. Suppose xi, xn are IID with distribution Pn in bold P, where bold P satisfies the Clough condition, which, in case you forgot already, this is the Clough condition, the uniform integrability condition. Then, then under Pn, square root n x bar n minus the mean of Pn divided by sigma hat n conversing distribution to a normal. So doesn't matter which sequence of distributions you take in this set of this family of distributions, any sequence will satisfy this. And then in addition, if you want to test the mean is 0 versus it is positive, then the t-test uniformly asymptotically level alpha, that is, this condition over here, holds. What we're going to do for the rest of the class, we're going to prove this. So let's get started. Any questions before we get started? All right, proof. First thing that we're gonna do is check this inequality over here. This equality, sorry, over here. A square root n x bar n minus mu is divided by sigma hat. Okay, and sigma hat here is problematic. So what we're gonna do is just simply multiply and divide by the true sigma. Okay, and then we end up with this piece. We have an element here that is the type of random variable that we want, which is that y random variable that we want. And then we have this element over here where y here is just x minus mu divided by sigma. Notice how we're doing, asymptotics for distributions that are changing with n, because we're taking sequences in this bold P set. So everything has this double index structure, and, parameters depend on this Pn. So we're going to look at, let's call this term 1 and this term 2. So for term 1, you can just invoke Lindbergh-Feller CLT. So we need to check the usual condition in this CLT, which says the lim sup as n goes to infinity of the expected value for Pn of the absolute value of 1, 8i square, indicator, absolute value of 1, y and I greater than epsilon times square root n is 0 for all epsilon, or any epsilon positive. Okay. But then note that this expectation is less than or equal than the expectation than the same expectation where you replace the epsilon and the n's by lambda, okay, provided n is large enough. Okay. But then this goes to 0 as lambda goes to infinity by our club condition. And so the condition that you need for the Lindbergh-Feller CLT is exactly the condition that you obtain from uniform integrability. And it follows then that square root n x bar nn minus mu pn divided by sigma hat nn, divided by sigma pn, conversion distribution to a normal 0, 1 as n goes to infinity under pn. So clearly all the action is going to be in this term, okay? Because the first part, term 1, just sort of like trivially follows from the Lindbergh-Feller CLT, given that you have this uniform integrability condition. So now we can say this object here converges in distribution to a normal 0, 1, which is essentially what we want to prove for the main term. So it must be that this object over here is the one that we want that converges in probability to 1. So to complete the argument, we need to show that, I'm going to flip it here because it doesn't really matter. The sigma hat nn square divided by sigma square pn converges to 1 in probability under pn, okay? And so if we write sigma hat nn square divided by sigma square pn, what we obtain is 1 over squaring sum from 1 to n x and I square divided by sigma square pn plus 1 over n square root n x bar and n sigma pn square, which is equal to 1 over n sum from 1 to n of x and I divided by sigma Pn plus little o Pn 1, because let's see if I can fit it here. This, okay, so I forgot to say something which I'm going to use. I'm going to say here, assume without loss of generality that mu Pn is 0. Okay, just so that I don't have to be subtracting mu Pn from all these expressions. Okay, nothing depends on this. It just simplifies expressions. And so if that's the case, you see then that this object here is the one that converges in distribution to a normal 0, 1. And since you are dividing by 1 over n, is little o P1. So what we want to show is that 1 over n, the sum from 1 to n of x and I divided by sigma square p square converges to 1 in probability under Pn. This is what we want. And if we prove this, we're gonna be good to go. Questions about this? So let me just go back 2 slides so that we know where we are. We want to prove this part of the statement, okay? Because notice that once you prove this, okay, this follows immediately. Because if this wasn't equal to alpha, suppose that you tell me the limbs of the supremum of this is not equal to alpha, then that means that I can find a sequence of distributions Pn such that this expectation is not equal to alpha under that sequence. So that means that this doesn't hold under that sequence. That contradicts the first part of the statement that says Pn is for any sequence Pn here, this happens. Okay, so the second part is trivial given the first part, and the first part requires this uniform convergence to a normal. Okay, and then what we said is like, okay, let's split the term that we care about in 2 parts, and then we already know that the first part converges to the point we want. All we need to show is that the second element just converges in probability to 1. And then after just simple manipulations, we show that that's equivalent to showing that this average over here converges in probability to 1 under Pn. Okay, so complete the proof by showing that, as I said, this is the second part. This is equal to alpha. Note that if the result fail, one could extract a subsequence Pn, okay, with Pn and P naught such that this will go to alpha prime equal to alpha, okay? But this would contradict the first part of the statement. So the first part of the statement gives us this kind of like trivially. So all the work is improving the first part of the theorem. So the lesson is that to prove the theorem, all we need is a CLT for triangular arrays and a law of large numbers for triangular arrays. And funny enough, proving, the CLT for triangular arrays is sort of like easy standard. We're even used to that. We use it in other lectures and so on. But this law of large numbers for triangular array is not something that, we use a lot. And actually, to my understanding, it was even developed after the CLT. Okay, and it is significantly more involved. Okay, so we're gonna look at that. That's unfair because we're not actually proving the CLT for triangular arrays. Okay, but you've done that with Joel. Did Joel do that in 480-2? You did, right? So okay, yeah. What? Nah, see, well, that's baby. So I'm being like too nice here, right? Doing the work for you. should have like 3 more problem sets where you do all this by yourself. All right. So, assuming there are no questions, I'm going to move to 2 lemmas. Lemma 1. That's yn1 to yn be IID with CDF gn with finite mean mu gn. And suppose that this satisfies the following condition. Is now a limit beta going to infinity, limit lambda going to infinity, the expected value under gn. Now we have the absolute value between y and the mean, okay, times the indicator that the absolute value of y and the mean is greater than beta, okay? So, and then this is 0. So you see that this is a different type of uniform integrability condition, okay? And the idea is that, you know, we're going to be needing a law of large numbers for square of random variables. So we want to be able to do that. You know, if we call our random variable this object, we need, and suppose you're assuming finite second moments to make it simple, then you're assuming that this random variable has 1 moment. Okay, so in a way, we're assuming 2 plus delta moments for the original variables. We need a a law of large numbers for 1 plus delta moments, because we're going to be applying a law of large numbers for something like this. Y is equal to x squared divided by this minus 1, which is essentially this second part. Okay, so the second lemma is apply the first lemma to the problem we care about. Let bold P be the family of distributions that define the Clough condition, uniform integrability condition. Suppose that x1, xn are IID with Pn being a sequence there, and that the mean is 0. This is just without loss of generality. Then under Pn, we have this converges to 1 in probability. And this is exactly the object that we had in our previous slide. So, lemma 2 gives us exactly what we want. And then just look at this thing over here. This is lemma 1 applied to this object over here. Okay, and what's not difficult, the easiest step, which I think I'm going to skip for now, which is later, because we're going to focus on this theorem, is like if x satisfies the Clough condition, then y defined like this satisfies this Bates condition. That's straightforward. So let's look at the proof of lemma 1. We're going to do the proof of lemma 1, and we're going to do it in 5 steps. Okay, let's go. Step 1. We're going to let Zn be defined as y times the indicator that the absolute value of y is less than or equal to n. And then we're going to show that the probability that y bar minus mn, which I'm going to define in a second, is greater than epsilon, is bounded by the probability that z bar minus mn is greater than epsilon, plus n times the probability that the absolute value of y is greater than n. Okay, so let's do this. This is the first step. So we're going to let mn be the expected value of z and I. And we're going to let z bar and n just be 1 over n, the sum from 1 to n of z and I. Remember, without loss of generality, we're going to assume that mu gn, which is the mean that we care about, is 0, just to get rid of those terms that are going to be annoying. So, where we can say mu of gn, which is 0, just expected value of y and I. You can write this, and this is a trick that is commonly used in a lot of different proofs when you want to deal with tail behavior. It's just a trim. So this is equal to the expected value of y and I times the indicator that the absolute value of y and I is greater than or equal to n, plus expected value of y and I times the indicator that the absolute value of y and I is strictly greater than n. Okay? Now notice this. This object here is z and I. And this object looks like the one in the spades condition. Oh, I don't know how to do spades. Yeah. Oh, that's kind of like it. Yeah. So we have that this is equal to mn plus this expectation. Okay. Now, second, I'm going to say know that the sorry. Note that the event absolute value of y bar n. I realize I'm using double n sometimes, and well, doesn't matter. This notation being somewhat sloppy, but the event, okay, this guy is greater than epsilon implies that the absolute value of zn bar minus epsilon is good. Minus mn is greater than epsilon, or the event that y bar n is different than z bar n. So notice to what I wrote. I'm saying if the difference between y bar and mn is greater than epsilon, then it has to be that the difference between z bar minus mn is greater than epsilon, or that these two bars, y bar and z bars, are different. Okay? And so then the probability that y bar n minus mn is greater than epsilon is less than or equal than the probability that z bar n minus mn is greater than epsilon plus the probability that y bar n is different than z bar n. And then also the probability that y bar n is different than z bar n. You can write as less than or equal than the probability of the union from y to n, that y and I is different than z and I. Okay, and this is less than or equal, whoops, than equal to the sum from 1 to n of the probability that y and I is different than z and I. And this is equal to the probability n times the probability that y and I is greater than n, because that's when these two are different. Then if you grab this inequality that we obtain over here, with this, we proved exactly what we wanted to prove in the first step. Okay? So first step is about proving some conversions, okay, of y bar n to not the mean that we want, which, in this case is 0 because we're normalizing to 0, but to this truncated mean, which we're calling MN, okay? Which MN is just this bar. Remember, we split the expectation in two, and so this MN is the truncated mean. And so we're going to show conversions to that truncated mean. But that's step number 1. Any question about step number 1? No question? Then after step number 1, it usually comes step number 2. Step number 2 says, show that this probability over here, that is the one is less than or equal than this plus this, where, this tau function, tau n of t is t times the probability, blah, blah, blah. And kappa n is just this over here. Well, this is an easy step. I'm going to say, recall, we just proved that the probability that y bar n minus mn greater than epsilon is less than or equal than the probability that z bar minus nm is greater than epsilon plus n times the probability that absolute value of y and I is greater than, what did I say? N. So, look. This is neat. It's just notation. This is tau n. N. By definition. This is our definition of tau n. Okay? Now the other term, we can say by Chebyshev's we have that the probability, the absolute value of z bar n is a bar here. Z bar n minus mn greater than epsilon, okay, is less than or equal than the variance of z bar n divided by epsilon square, okay, which is equal to the variance of z and I divided by n epsilon square, okay, which is also less than or equal than the expected value of z and I square divided by n epsilon square, okay? And so this is 1 over epsilon square times 1 over n times the expectation of y and I squared times the indicator of the absolute value of y less than or equal to n. I'm going to say here, let me change color, because we define z and I as y and I times the indicator that y and I is less than n. Cool. So now you look at this, and this is 1 over epsilon square times kappa n n. Because this object over here is exactly the definition of kappa that we have right there. Right? We're going little by little. Any questions about step 2? So if you have to guess, after step 2, we have step 3. You got it right. You guys are smart. Step 3, okay? Remember, this is tau and this is kappa. So claim is that using integration by parts, you can show that this kappa function is negative tau t plus 2 over t integral from 0 to t of tau x dx, okay? This step, I'm going to skip. You believe me? So therefore, in order to show that the probability of y bar n minus m converges to 0, it is sufficient to show two things. Since this guy is less than or equal than kappa plus tau, then we need to show that tau goes to 0. And remember, here kappa is just tau, so tau goes to 0 plus this integral. So the other piece would be to show that this integral goes to 0. So I'm going to start here. I'm going to start showing that tau n n goes to 0. So what is tau n n? Well, tau n n by definition is n times the probability that the absolute value of y and I is greater than n. Okay? This is less than or equal than, or if you want, let's just do one step more. This is n times the expectation of the indicator that absolute value of y and I is greater than n. Okay? And this is less than or equal than the expected value that the absolute value of yn times the indicator is greater than n. Right? Because we're considering that event where the absolute value of y is greater than n. So we have that inequality. And this goes to 0 as n goes to infinity by the Spades condition. I want to see if your spades look as nice as mine. So then, remember what we proved before is that the probability of y bar n minus m greater than epsilon was less than or equal than tau n n plus epsilon negative square kappa n. So we want to show this goes to 0, this goes to 0. This we already done. And this one has two parts. The first part already done. So all that remains is this. Is this integral, okay, going to 0. And that is what we're going to do in step number 4. Step 4, this integral goes to 0, where tau is this object over here. All right? Let's do it. This is slightly trickier, but we're almost done. We're almost home. Okay? So, let me write 2 n integral from 0 to n of tau n x dx. Okay? It's going to be less than or equal than 2n integral from 0 to n. And I'm going to use this inequality that we have over here. Okay? Integral of the expected value of the absolute value of y and I times the indicator that the absolute value of y and I is greater than x dx. So let delta positive be given. Okay, this is arbitrary. Two parts. I'm going to say A here. Let n naught n beta naught, okay, be such that the expected value of absolute value of y and I times the indicator y and I greater than x is less than or equal than delta divided by 2 for n large, particular n greater than n naught, and x being greater than beta naught. This follows from, I'm going to write it here again, this club condition, right? Because the club condition says that this goes to 0. So let me just pick an n large enough and a, x large enough so that this happens. Okay, good. So now B for x less than beta naught, we have the following. Expected value of the absolute value of n and I times the indicator that y and n I greater than x. Well, this is for this is less than or equal than the expected value of the absolute value of y, right? And so now I'm gonna split it again, but using this value beta naught that we're saying. Okay. And this is less than or equal than delta divided by 2 plus beta naught. So here comes the last part. Let's see if I can make it fit. Yeah. Where is it? I'm gonna grab this object now. Okay. So it's gonna be 2n, the integral 0 to n of this thing, which I'm not gonna write dx, to see if I can make it fit. It's just gonna be 2n, the integral from 0, okay, to beta naught dx plus the same integral from beta naught to n. And so this is going to be using the previous two results. It's just going to be less than or equal to 2 whatever 2 over n beta naught plus delta divided by 2 plus delta, and this is less than or equal than 2 delta for n large. So since delta was arbitrary and given, and we show that this integral is less than or equal than 2 delta, we then show that the integral from this object over here goes to 0. Questions about step 4? Well, I said there were 5 steps, so we are getting to the end. We just put all this together. Step 5, from this to what we want to prove. Okay, so let's call this, whoops, I didn't want to do that. Let's call it star, okay? So from star, we have that y bar n minus mn converges to 0 in probability under gn, okay? Well, then, we also said here we had also, I want to say, we had in the first slide 0 equals mu gn, which is equal to mn plus expected value of y and I times the indicator y and I is greater than n. Oh, I'm sorry, this is not right. I'm jumping ahead. Plus the expected value of y and I, indicator, the absolute value of ni greater than n. And so the absolute value of mn, or if you want, the absolute value of mn minus mu gn in this general case is less than or equal than the expected value of the absolute value of ni times the indicator that the absolute value is greater than n. And this goes to 0 due to the space. Oh, that didn't look right. Oh, my spades are not. The spades condition. Okay, so how do you do this? Triangle inequality. Mu bar minus mu gn less than or equal mu bar minus mn plus mn minus mu gn. This goes to 0. This goes to 0. All this goes to 0. And we completed the proof. Questions about this? If we put together what we have done so far, we have that the t-test is something that is going to control size uniformly well. We have this lim sup of the supremum of the rejection probability is bounded by alpha. It's actually equal to alpha in this case in the limit. So the t-test is a size equal to alpha, asymptotic size. Now, this wouldn't be very useful if we don't say anything about power, because, as we saw when we talked about Bahadur-Savage, when we talk about impossibility of testing, is that if you control size, you don't have power. If you have power, you don't control size. So we just show that the t-test controls size. Now we need to argue that it has powers, because again, as I said, we can always flip a coin with probability alpha, and that test will just, be uniformly valid all the time for any distribution and so on. It just doesn't have any power. So, power of the t-test. I wrote, so far we know that the t-test behaves uniformly well across a fairly large class of distributions. We now study some power properties of the t-test. In particular, we will show that the t-test is uniformly consistent in level and derive a limiting power calculation. The result is summarized in the following theorem. Let bol P be a family of distributions satisfying the Clough condition, which is the uniform integrability condition, and let bol P not be the set of distributions in bol P with mean equal to 0, which is assumed to be non-empty. Then, for testing the mean equal to 0 versus the alternative that the mean is positive, the limiting power of the t-test against sequences in bol P such that square root n mu divided by sigma goes to delta. So you can see that these are a sequence of local alternatives, or in the terminology that we learned already, these are contiguous sequence of distributions. Then the limit of the rejection probability of the t-test is 1 minus the CDF of a normal at the quantity of a normal minus delta. Okay? And in particular, if you just take the infimum of all the distributions that have this local parameter at least equal to delta, this is the power that you have. Okay? And so this is strictly greater than alpha for delta positive. And the t-test has non-trivial local power. The proof is straightforward. Like x1, xn be IID distribution Pn, and consider the t statistic, which is the one here I forgot, this is a mistake. Here there's a square root n missing. Nice. Right, Tn equals to square root n x bar minus the true mean divided by sigma hat, and then we add the true mean that we're subtracting here, so we end up with this term over here. And so notice this, the denominator here will converge to 1 because bol P is we have this law of large number which is proof for bol P, and then the numerator here converges to delta. So this guy is center. So this guy converges to a normal with mean delta and variance 1. Okay, which is what I wrote over here under Pn. And from here, the result that we just wrote follows. To prove the second part, argue by contradiction, okay, and assume that there exists a subsequence Pn with this guy greater than or equal than alpha, and suppose that this converges to something that has smaller power than the one that we wrote. Well, this would violate the first part if, you take this sequence and has a limit equal to delta, okay? So, and if it that, as I wrote here, if does not have a limit, then pass to any conversion subsequence and apply the same argument. A lot of these proofs, as I said earlier, work with sequences, and then sometimes the only problem is that certain objects that you're studying may not converge, so which complicates the analysis in the limit. So you just pass to some subsequence until you have a subsequence that converges, and most often that's enough because these arguments are typically proven by contradiction, by arguing that there exists a subsequence that creates some problem. And so that's how you do it. So in some papers you see, and even guilty of that in some papers that I've written myself, if you're too explicit about the sequences, the subsequences, and subsequences of the subsequences, the notation starts being annoying. So, I think it's better to just say a subsequence and take maybe a further subsequence, but use the same terminology, which is Pn. As opposed to PNK, PNK, NK, 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 and then just keep taking subsequences that just annoy the notation. All right, and that's about it. So as I said, I promised that today we were gonna finish earlier, and there's no point to add in more material. I think the class today is important because it shows us under what conditions we can rely on the t-test. And in particular, moving forward, what I want you to have in mind is that we proved that the t-test was not uniformly valid for certain testing problems, but this is one of the examples where I will phrase as a technicality condition. Of course, when this was initially studied, it was very important. But by now, where we have a good understanding of this, nobody will question that the t-test is not uniformly valid. We understand that we need to restrict the DGPs, okay, so that we have something that works uniformly well. And so when we come up with examples later on, for example, in moment inequalities or other type of problems in which, we're going to say that certain tests, perhaps based on things like the t-test, the wall test, the likelihood ratio test, are not uniformly valid, we're going to run into issues that are going to be more complicated, or if you want, more substantial than the ones that we discuss here, where you just save everything by assuming that the family of distributions is smaller. We're going to have to do more work to make tests work in more sophisticated settings. So this is one of the things that I would call a technicality, okay? And that's why in many settings like this, people just prove point-wise asymptotic convergence, because they're going to say, look, just going to prove that the test is point-wise, okay? As we know that, if you assume then 2 plus delta or whatever it is, uniform integrability, you get uniform behavior. Okay, great. And so that eventually may lead to problems, as we are going to see in the future lectures. For now, I'm going to stop and I'm going to address questions that you guys may have.